we've been looking at finding where our function is increasing and decreasing, and we found that we could do that with finding out where our first derivative was equal to 0, and then testing our intervals by plugging values back in to see if it was positive or negative. We found that if we plugged a number back in and to the first derivative and it was less than 0, then it was decreasing. The slope was negative there. And if we plugged a value in, let's say b, and it was greater than 0, then we found that the function was increasing at that value. So the second derivative tells us the rate that our rate of change is changing. So is that increasing function going faster or kind of growing at a slower rate? So second derivative tells us the rate of change of the first derivative. And that is going to depend on, is it the graph concave up or concave down? Okay, so concavity. So if it's concave up, it kind of looks like a parabola facing upwards. So this is concave up. And this is when the double derivative is greater than 0. Concave down, to me, it looks like a parabola kind of facing downwards. This happens when our double derivative of x is less than 0. So to me, I think about it, greater than 0, your bowl can hold stuff. It's positive, it can hold stuff. If your bowl is upside down, that bowl can't hold anything. It's negative. That's how I remember which one is concave up and which one is concave down. So let's look at a couple of different examples, right? Because we can do a chart. And if we looked at f prime of x, let's say that that was greater than 0. And the double derivative was also greater than 0. And let's say that this occurs on some interval. AB. So I know that my function is increasing, but it's greater than 0, so it is concave up. So I have to look at something that is increasing, but concave up. So notice that the shape here, increasing, whereas that concave up, increasing, it looks like this. So that piece of the graph on AB is going to look like the following shape. Where if our function was increasing f prime of x, and the double derivative was less than 0. Well, it's increasing. So it's again going upwards. But the double derivative is less than 0, so I know that the shape is concave downwards. So look at this piece of the graph and where it's going, increasing, but it's concave downward, so that general shape is going to look like this. So this is what it looks like to be increasing, but concave downwards. So let's look at it where our original function is a decreasing function. So let's look at f prime of x is less than 0. But the double derivative is greater than 0. So if I think about it, my original function would be decreasing on that interval AB, but double derivative is greater than 0, so it has to be a concave up shape. So looking at decreasing and concave up. So decreasing, so it's going to have to look like this. So that's what the shape of decreasing concave up would look like. In the last case scenario is where our first derivative is still less than 0, so it's decreasing, but our second derivative is less than 0. So we have something that is decreasing, but second derivative is less than 0, so this is concave down. So look at the piece that is decreasing here and concave down. So this was, our graph would look like this shape on that interval. Okay, so now kind of knowing what we're looking at, we're going to look at a graph and find where it's concave up and concave down. But before we do that, that point where it changes direction from concave up to concave down, that has a special name, and that's called an inflection point. So the inflection point is a point on our original function where the graph changes concavity. Okay, so let me just show you what that could look like. So here's something that's concave down, and now I'm going to change it so it's concave up. So that first piece is concave down, and then it's going to change direction in here. So in here, it's changing to concave up. So that point where it's changing is the inflection point. Okay, so looking at the graphs, we're trying to figure out where is this graph concave up and concave down. So we're looking at the intervals. Recall the intervals we're looking at are the x values. So where is that x value? It starts to be concave up and stops to be concave down. And there might be multiple places. So let's look at this first graph. So looking at this, I notice, let's do concave up. So that's where the parabola kind of looks like it's facing upwards. And so notice that this piece in here, we're coming from negative infinity, and we're changing at A. So we're going to go to capital A. Union. I notice though, again, it's concave up on another piece of this graph, starting at B, and then it's going to infinity. So parentheses, b, comma, infinity, end your parentheses. So in here, it's concave down, starting at A and going to B. So parentheses A, comma, B, parentheses. Okay, so again, so let's go to the second graph and look at concave up. So looking at this, it looks like it's starting to be concave up here when x is -1 to about, I would say here, x is +2. So -1 to +2. And then again, it looks like it's changing maybe around 6. So union 6, x is 6 to infinity. And then it's concave down. So -infinity until we hit x is -1. Union x is 2. All the way to x is 6. So recall, those intervals are just looking at those x values. On those intervals. It has nothing to do with the y values of that interval. So you should be able to look at a graph and find what intervals the graph is concave up and concave down. You should also be able to find your inflection points. So inflection points on that first one would be at our value in x is A and our value in x is B. I don't know what the y values are of that, so I don't actually have the point. Same here, it doesn't have a y value units, but I can see it's when x is -1, when x was 2, and when x was 6.